To the NetBSD Foundation, the Asia BSD Con community members, and Hrishikesh and Saredo, and above all the audience here. The first thing I would like to say is thank you. Thank you so much for inviting me here. I'm so honored to be here today. Myself is Hrishikesh. I started contributing to NetBSD last year by being the part of Google Summer of Code 2016. I pursued my BTech from NIT Warangal in Computer Science and Engineering. I'm 2016 pass out. So my project is about Ext4 file system implementation in NetBSD kernel. So in the Google Summer of Code, I implemented two features of Ext4 file systems, which are Ext4 extend and Ext3 directory index. So today I am going to describe about the features that implemented in that project. So before that, I would give you a brief background of VFS layer of NetBSD, and then I'll jump to the specific features. So let's get started. So the two things, a concrete file system and a virtual file system. So basically a concrete file system is the actual file system, the module of the kernel which controls the data to store and retrieve from the disk. So this is the actual implementation of the file system, which actually takes care of the strategies to store and retrieve the data. And whereas the virtual file system, in virtual file system, it's like it's an abstraction over all the concrete file system in the kernel, so that the rest of the kernel has only to deal with virtual file system, and it don't need to know the exact implementation and the functions which a concrete file system implements. So these are the main differences. So let's talk about the VFS layer of NetBSD. In a virtual file system of NetBSD, it's basically composed of two things, which is a virtual file system interface, VFS interface, and vnode interface. These two are the main two parts of the VFS layer of NetBSD. And where VFS layer resides in the kernel? Here we have user level processes also. So basically user level processes deals with the system call interface, and system call interface in turn invokes the exact subsystem of the kernel, like any system call related to memory management will invoke or will deal with the memory management submodule, and file system related calls like open, read, write will deal with the virtual file system submodule. So in that way, system call interface is the uppermost layer of the kernel, and after that we have the VFS layer, and that VFS layer actually deals with the actual concrete file system. So here we have a number of implementations of the file system. So basically the rest of the kernel here, system call interface and other modules of the kernel only knows and like deal with the virtual file system here. And so every concrete file system is implemented above the buffer cache, which is like exact disk like utility, but it optimizes the redundant disk access for the same data using caching. So it's like directly above the disk, but it's a caching. So every file system is implemented above. So every file system is implemented above disk and a buffer cache. So as I said, the VFS layer in NetBSD is composed of two interfaces. First is vnode interface and VFS interface. Vnode interface is basically a structure which is an abstraction over every active file in the kernel. Like any file which has been loaded into the kernel will have one vnode associated with it. Vnode would contain some metadata about the file, and irrespective of their actual type of the file, like a file maybe of type text file or any audio, video or any external device as well. So these metadata are independent of the underlying file, and some abstract methods which is to be implemented by the concrete file system underlying that. So vnode is basically is a you can say structure and abstraction for the rest of the kernel for every file. So and VFS interface is basically as the same we have vnode for the files. VFS interface is an abstraction over every file system in the kernel. So we may have different file system, like every file system has its own strategy to store and retrieve the data. So based on that, we may have a number of file systems. So VFS interface is basically an abstraction over all those file systems. So VFS layer is basically composed of two things, and these names are sometimes used interchangeably. We basically call VFS layer for whole virtualization, and in that VFS interface is the things that exactly deals with the file system operations, and vnode interface basically deals with the file specific operation. So VFS interface may deal with the file system specific things like mount, remount, or write super. Super block is the metadata. It's a structure which contains the metadata about the file system itself, like block size or the underlying hardware device ID. So in that, here we have VFS interface would contain all the metadata methods which has to be performed over the file system, and vnode is basically for the same things but to be operated on with file. So in VFS, so that was the VFS layer of NetBSD we talked. Now I'll give you a very brief info of Ext4FS. Ext4FS basically introduced many new features like bigger file system and file size. Earlier in Ext3FS we used to have one limit over the maximum file size, like some 1 or 2 TB. So now it got increased to 16 TB I guess, and file system size in Ext3FS was around 16 TB. So now it's 1 million TB, 1 exabyte, and subdirect escapability is also in the Ext3FS. Some limit was there, and in Ext4 it's theoretically unlimited number of files is supported. Ext4 extend, that is the feature that I have implemented. We're going to talk about this in detail. Multi-block allocation is it's again introduced by Ext4. It is like whenever a file is to be created or data has to be write in the file, first the file system has to request for the free blocks, so where the data can be written. So for that, file system asks for some to get the free data blocks. So for that, let's suppose the file is of some 100 MB and each file system block size is 1 MB. Then that file would require 100 blocks. So for that, the earlier in Ext3 for each of 100 blocks, file system has to request them separately, like one by one, 100 times. But in Ext4 it introduces directly 100 blocks to get the empty 100 blocks in one shot. So here we can have some optimization with the allocation. Like we can, if we know that all the 100 blocks has to be allocated for one single file, then we can create them in one place, so that it's not very sparse over the whole disk. Ext3 directory index, it's basically a Ext3 feature, but I have implemented it, so I put it here. We are also gonna talk about this. And in Ext3, the state of Ext4 in NetBSD is like, it's not a different file system implemented in NetBSD. It's the Ext2 which is the base file system which is implemented, and a few features are Ext3 and a few features of Ext4 has been implemented in Ext2 only. So it's not a different file system in NetBSD. Yeah. So let's start with the feature that I implemented, Ext4 extend. Ext4 extend feature is basically an efficient way of indexing file data blocks. So first question is, why do we need indexing of file data blocks? So let's talk about first what is a file and why do we need the indexing. So let's suppose there is a file, then the file would contain the actual file data, some metadata and its name. So when you open a file, you will get only file data. You won't get the metadata and file name inside the file. So where does that the metadata and file name go in the file system? So it's basically as we have talked about vnode, which is an abstraction of every active file. There is a inode in a file system, not in kernel. It's a inode is specific to a file system, which contain all the metadata about the file, and an index that I'm going to talk about. So here let's consider a file of size, let's suppose 12 KB, and let's suppose the file system block size is 4 KB. Then that file would require 3 blocks, right? So all those 3 blocks can go anywhere in the disk, right? So they need not be all together. Let's suppose this disk and the blocks specific to this file are placed here, here, here. So let's suppose the first block is at 301 and then 555 in that manner. So while reading the data, how would file system know that where is the file data has been placed in the large disk, and like how to read those particular blocks? So for that, file system, each file has a mapping which stores the file data block number, like so like here 1, 2, 3. These has been mapped to the actual disk block number. So here 1 has to be mapped with 301, 2 has to be mapped with 555 in that way. So this mapping is the file data block mapping, and we can have many strategies to construct this mapping. So in Ext2 there was indirect pointer approach that I'm gonna talk about. So basically an inode, which means that index node, which contain that indexing. Most importantly, it is mainly to store the index and some metadata about the file, which are like file size or owners or permissions, like that, and the inode number. This is also a unique inode number in the file system. So here we need a inode for each file in the file system, and that's why we need indexing for mapping the file block number to disk block number. Yes. So how does Ext4 extend efficiently map the file blocks, file data blocks? So first we see the Ext2 approach of mapping. So what does Ext2 does is, for that indexing, usually we have very less space in inode, because inode contains some metadata, and this mapping, this has to be like in as less space as possible. Otherwise that inode would become a file, and that we don't want, right? So here we have limited space, and in Ext3's file system we have 60 byte for file that index in the inode. So basically in inode we have just 60 bytes to map all the file data blocks, and that file data blocks can be composed of millions of pointers, because a file can be any of any size, like as much as millions bytes. So how does Ext2 manage the mapping from logical block number to physical block number in just 60 bytes? So it is basically in 60 byte. This is the particular field, that 60 byte field in the inode. It has 15 pointers, each of 4 bytes, and in that there are 12 direct pointers, which is like directly point to the actual disk block number. So for the file like sufficiently small, which contain only 12 blocks, we have the direct 12 pointers, and that's it. So in that way the small file can be mapped. And what about a file composed of thousands of blocks? For that it has one indirect pointer, and then one double indirect pointer, and then one triple indirect pointer. So in that what happens is, for the indirect pointer here, the 4 byte pointer, it doesn't point to directly the disk block, but it points to a block inside the disk, which actually has the exact pointers to the file data blocks. So here this particular block, this resides in the disk, the same disk, but it is not, it doesn't contain the actual file content. What it contains is again a list of pointers, and they are pointing to actual file data blocks. So here after 201, the next file data block is 213, and which is stored here, and which again pointed by here. So in that way, in one block we can have according to 4 KB block size, and each pointer size is 4 byte. We can have here 1000 pointers. So file of that size can be mapped in that way. And again, if file is even more bigger, then we'll have one double indirect pointer, which is two-way indexing. Like here each pointer will again point to the next block, and they are in turn the exact pointers of the file data. And next we have 3-level indirection. So in that way Ext2 and 3 provides the mapping in just 60 bytes for sufficiently large file. But the problem here is for sufficiently large file, we need to go through all these indirections, and that is inefficient. So like for accessing the any particular block, we need to first access the inode, and then from there to one disk access, and then again another disk access, and then the exact the data we was requested. So here it's kind of overheading. So how does Ext4 extend manage to have the same mapping efficiently? It's basically, as we saw in the Ext2FS indirect pointer approach, there is a one pointer for each file data block, but it doesn't happen in the Ext4 extend. Ext4 extend basically has one pointer for a bunch of contiguous file data blocks. So let's suppose at one location we have a bunch of blocks like 100, then we'll have only one pointer, and which will point to the initial, the very first block in that group, and will have the count that starting from here, the next 100 blocks, say the part of the file, and on the top of that it is BA+3 indexing. So it's again efficient in the way of the traversing time. So this is a typical extent tree. So let's suppose there is a file, and this I_data is the same field, 60 byte field in the inode, and let's suppose a file is consist of a number of disk blocks. So here we'll have we can have like a number of contiguous file data blocks, and then some space, and then again the blocks of specific to these this particular file. Like it can be fully sparse or dense, like it depends. So it is efficient in those cases where the file is sufficiently dense, like it is all the file data blocks, or not all, it's like a big group of file data blocks reside at one place and in the bunch of groups. So what happens here is in the extent tree there is there are two type of nodes, and for each node we have one disk block. So this is a node of the tree, and it is allocated in a single disk block. So this whole is a disk block, and in that there is, for each header, for each node there is a header, and which contains some metadata about the node. And there are basically two types of nodes: internal nodes and leaf nodes. Internal nodes has different structure, and leaf node has different structure. The header is common to all, and the difference among the internal nodes and leaf node is basically after the header, leaf node has extend structures, whereas the internal node has the extend index structure. So extend structure is composed of two fields. One is, as I have already said, the initial address of the block, and the number of the count, which is like number of contiguous data blocks starting from 100 for this case. So this particular pointer is a single pointer for 100 for 5 blocks starting from 100. So we don't need to access one pointer for each block here. Once we have got this 100 as the address of the disk, we can then directly access 100, 101, 102 till 104. And in the internal nodes, what happens here is each internal node is composed of header and Ext4 index, extent index, which is basically a pointer to extent index node, which is like internal node or a leaf node. So we can further here have a internal node level, or it can be directly to pointing to a leaf level. So for lookup operation to get the file data blocks, will basically start from here. This is the root. The header will tell the how many blocks we have here, how many structures we have here, basically how many pointers we have here. And let's suppose a file is like, for the same case, let's suppose the file is 1000 blocks, and if we have all the 1000 blocks, as the Ext4 also supports multi-block allocation. So if that multi-block allocation feature allocates all the blocks together, all the 1000 blocks together here, then we'll have just this one pointer, and this one pointer will be pointed here. So this particular extent index will be replaced by this extent, which is 105, that would come here, and that single pointer will represent all the 1000 blocks. So like as many groups we have, contiguous groups, so here we have two groups, so here we need only two pointers, and this I underscore data field structure itself, these are the 60 bytes, that itself can contain 4 extent structures. So like 4 groups of the data blocks, file data blocks. We don't need this tree at all. Like for those 4 groups, all the 4 pointers will come here, and we'll have in that 4 pointers we are representing the file maybe like of 1000 blocks or even larger. But the thing is, we can only represent the 4 pointers here. So if we like file is grouped into more than 4 groups, or then we'll need this tree, and this extent structure will be replaced by extent index structure, which is here. So basically that feature that Ext4 extent we just now saw was already implemented by FreeBSD. So before starting my work, I thought of looking at the FreeBSD's code. So I found that it has been already implemented in FreeBSD, but the major difference between NetBSD and FreeBSD's VFS layer is the approach of handling double cache problem. So that is the thing which makes the major difference in VFS layer of 2 kernels. So we'll talk about first what is double cache problem. Yeah. So basically, for any application in user land, any process or any system call or utility in the process in the user land, it's like for accessing file data, we have 2 major approaches to access file data, which is mmap system call or read write system call. So read write basically just give you the file data in a buffer, and mmap will map your process memory to the file so that you can access the file directly as you are accessing your process memory. So but those 2 utility to access the file data are implemented above 2 different subsystems of the kernel. So mmap is basically implemented above the virtual memory interface, UVM, and read-write system call is implemented above the I/O subsystem. So these two subsystems, virtual memory subsystem and I/O subsystem, has their own caching mechanisms. So both are having their own caching. So basically, virtual memory subsystem uses page cache, and the I/O subsystem uses buffer cache. So basically, page cache and buffer cache are implemented at different levels. So they are not in the same level. And as I said at the very beginning, buffer cache is exactly disk-like interface, which only the only difference between those two is here we have the caching, but it is exactly looks like the disk. So this is the lowermost caching. So page cache is basically about that. So for getting any for getting the data stored in any disk, we first the data has to go through buffer cache, and for this particular cache, this particular case for M mapping, it has to go to page cache as well, and then to application. So in that way, we are like we are caching the same data twice for this particular flow. So here we are like it may create many problems like memory inefficiency, or we are wasting CPU cycles, or it may even gives the inconsistency of the data. So basically here we are doing the redundant job, and but because those two subsystems are implemented at different time and different at different levels, both the caching is required. So different kernels has their own approach to get around with this problem. So this is the double cache problem. All those difficulties we call them as the double cache problem. So in the FreeBSD, the approach to deal with this problem is FreeBSD basically gives the same physical memory for both page cache and buffer cache. So the code above the memory interprets them as the page cache for the virtual memory subsystem, and buffer cache for the the FreeBSD approach is to allocate same physical memory for both the subsystem, for both the caching, and the above code, the code above the physical memory would interpret them, one as the page cache and another is as buffer cache, but the actual physical memory is same. But the NetBSD's approach is to use the page cache only instead of using buffer cache, and it has been introduced. This concept has been introduced by UBC interface. So we'll talk about next what is UBC interface and how it provides a strategy to deal with double cache problem. So what happens in UBC is basically introduced 2-3 new functions which are like has to be implemented by file system developers, and that itself will get the data into the directly pages without going through the buffer cache. So here from the raw device, data directly comes to the page cache, and from page cache the M mapping happens as the usual manner, but from page cache UBC provides a way to get the data for the read-write system call. So basically UBC is not exactly here, it's like kind of both. It's also includes the getting the data from raw device to page cache. So M mapping after the page cache happens in the normal way. UBC is unified buffer cache. So here we'll see the how UBC gets the data directly into page cache and without going through double cache, buffer cache. So for the we'll see first for mmap memory mapping. When any user request for a data mapping, file data mapping using mmap, the request goes to UVM, and then UVM basically invokes VOP get pages and VOP put pages. These two functions has to be implemented by file system developer, because only specific file system developer knows what is the approach to get the data and store the data inside the file system. So here UVM directly invokes these two functions, and these two functions are basically take care of like getting the data from here to store it and to get the memory data block mapping, file data block mapping, and then writing to the disk. So put pages will have the pages containing the data, and it will write to the disk and going through the specific file system code. But the thing is here VOP get pages and put pages are directly deals with UVM, but the file system developer may not know about the UVM specific code. So what happens is in the kernel has already implemented some generic functionality of get pages and put pages. So like most of the things remain same for all the file systems. So but the actual mapping from logical block number to physical block number, that is actually depend on the specific file system. Rest all the things like handling page fault, getting the requesting for the pages, and then write back to the disk, all those things remain same. So here kernel has implemented the generic functionality, but it invokes VOP bmap and VOP strategy functions for getting the actual mapping for the mapping that knows the logical block number to physical block number. So here everything is implemented here, and the kernel invokes VOP bmap, which is file system specific mapping, and the VOP strategy is basically for the pages which are not inside the file. VOP strategy is invoked first, and if data is already there in the page, it has been requested already, so it would be there in the page, then it would directly return it. If it is not there, then it will call the bmap to get the actual mapping, and then it will get those data from the file system and will transfer them into the pages, virtual memory pages, and then it will return. So here get page and put page, basically the job of get page and put pages is to allocate the pages and then to check if data is already there. If it is there, then return it. If it is not there, then get the file system specific mapping, and then read the once we have got, here we'll get the disk block number. Once we have got the disk block number, we can directly call the VOP strategy of disk. So VOP strategy is here, it's not a recursive call, it's a VOP vnode of disk. Here it was vnode of file system. So VOP of disk would directly give you the data. It is implemented by the disk driver. So what happens for the read-write system calls? For that, here the actually UBC comes into for the read-write system call. Previously we were calling this to the buffer cache mechanism, and the B read and B write would give you the required data. But here we are not calling to B read and B write. Here we are calling the methods which are provided by UBC interface, UBC allocate and UBC release. These are kind of B read and B write functions. Here the UBC itself, UBC allocate will itself allocate the pages, and then those pages request would go to the UVM. So here the flow is same again. So basically for both the utility, UBC maps them to a single flow so that data don't have the redundant caching. And this whole thing, even this whole thing we call comes under UBC. So this was the Ext4 extent mapping, and we saw the differences in the handling of UBC interface and handling of double cache problem in the two kernel, and the differences was one is using same physical memory and another is using UBC interface. So this was the mainly difference between the VFS layer of two kernels. So what I have to do is to get the code from FreeBSD, which is implemented above buffer cache, and I need to port it in the UBC interface. So basically for the exact mapping part, I got the Ext4 extent specific code, which mostly remains same irrespective of the underlying kernel. I got the code from there, and the mapping specific part I need to put it here in the B map. And for B read and B write, which was implemented above buffer cache, I needed to implement our UBC allocate and UBC release. So this was my job. I just got the core extent mapping code from there, and I mainly focused on to somehow fit that code in here. Ext3 directory is an efficient way of mapping the directory entries. Like we have in the directory we have a number of subdirectories or files. So all those files are basically stored as the entries in the directory, and directory itself is a file, and which is like exactly a file. It has all the features that a file has, like inode, it has inode, it has some metadata about the file, and it stores all the files, subfiles, subdirectories in a list fashion. So for all the files, we'll have here the corresponding entries. So that entry would contain only the file names or subdirectory names and not their data. So here we have a list of directories, subdirectories or files, and so that entries can be a list can be of type linked list or array. So in Ext2FS, the directory structure is it is a list of kind of linked list. So since it is a linked list, all the demerits of linked list applicable here. We have a sequential reading time. We don't have random access here. We don't have we have different memory for each node. So because of the file, file can be of variable length, file name can be of variable length, each node will have different memory. So because of that, we can't have the uniform memory for all the nodes, and that is why Ext2FS uses linked list. And then how Ext3 implements that as the as an array, and makes the all the nodes of equal size, and so that it is efficient. So basically it replaces the directory entries stored in a linked list to a tree, which is we call here hash tree or H tree. And H tree is basically is a B tree, and the keys for that tree is the hash of the file names. So for any file name, we'll first calculate the hash value of that, and then from that hash 2 will create the H tree, and with the key as the hash values. And the tree will have two different types of nodes. The leaf nodes here we call directory entry blocks, and internal nodes are basically directory index blocks. So we'll see here the this is a H tree. Here we have this is as the directory entry blocks, and these are internal nodes that stores the index. So what happens here is in the H tree we have the leaf level exactly same as the linked list that we used to have in Ext2FS. So this is exactly kind of the linked list, and these internal nodes are like the points to the leaves here, and the hash value here stores the minimum hash value of all the entries present in one node. So it would consist of like some hash value, and that would represent the minimum value of all this, and the hash value stored here will be sorted according to their hash values, and the corresponding block number will point to the next block. And since they are having same memory and they are sorted, it's kind of array, sorted array thing. So here we have binary search applicable. So for getting any file for ls, we need to travel this tree, and at every step we'll first calculate the hash value. We'll first compare the required hash value with the current node hash value. If it is lesser, then we'll go ahead and in a binary search fashion, and once it matches or it is the just lesser than the target hash, will pick that block pointer and will travel the next level, and there will search the directory files in the linear manner. So here again we'll traverse the node in linked list fashion. So basically up to here we are optimizing the traversing time from linear to log n. So here we are using binary search, which is log n, and the depth of the tree is again log n. So the whole traversing time from n square to we are making them as n log n. And there is a fake directory entry concept which is used to support the backward compatibility with the Ext2FS directory structure. So here we have fake directory entry, which is basically will represent as the will act as a entry to deleted file. So and it will point to the next entry, next block, and the linear that Ext2FS algorithms it is basically giving an illusion to Ext2FS traversing mechanism that the whole block is empty and just skip this node and come here. So in that way it supports backward compatibility as well. So this is the Ext3 directory index implementation. So now I would like to have questions.
Does Ext4 have any protection against complexity attacks against HP implementation? Like they are using, you said something like a 32-bit hash, so it's very easy to create 100,000 files in a directory that all having the same hash. So this tripling rates back into a linear directory list.
For that, basically, I think I need to make some progress on this, because I just implemented what it was there in the FreeBSD's code. They are handling it as, they are assuming like we won't have much collision because the hash algorithm itself are very optimized. They are using MD4 and two other hashing mechanisms. So it's like kind of hashing over hashing. So like in that way, they are, for now they are skipping those things. I don't know like if it is fully secure or not. I'll have some progress on this and then I can get back to you. Any other? No questions? Okay, awesome. Thank you.